Chapter 12, we are covering linear regression and correlation. And chapter 12 is fairly short, but it covers talking about relationship where it's a cause and effect relationship between two variables. So in this chapter, we're going to learn how to create and analyze scatter plots. And that's something that might be familiar to some of you already. We will perform tests to determine if there's linear correlation. And this chapter will allow us to test claims about linear relationships between two variables. So this is when we're saying all of our data points have kind of an X and a Y, and we're thinking that X causes Y. And so we're looking to see if there's some sort of relationship there. And so we would be able to draw something called a scatter plot with each of these. So sometimes when we collect data, we suspect it might be related in one way or another, that one is affecting the other one. And each data point would have an X value and a Y value. And we'd be able to plot these to see if there appears to be a relationship. So you would have X-axis, Y-axis, and then all of your data would get plotted something like that. And we're looking to see if, is it possible for us to draw a line that's going to kind of fit the trend of most of them, be fairly close to most of them. This one that I drew is kind of scattered out, but it kind of looks like a line with a positive slope is going to fit it. Some sort of line there would kind of fit the overall trend, but not very well. So this is kind of what we're going to do this chapter is say, okay, I have all these dots plotted. Now, is there a line that I could draw? And if so, what is that line? And then how good is that line? How close to the line are all the points? How good is that line going to be at predicting? And is it close enough for us to say that it's actually a linear relationship? So that's what we're looking at in this chapter. So here we have 5 different scatter plots that we're going to kind of take a look at. This first one up here, we can see a fairly positive linear relationship. And it's a fairly strong relationship as well. We could take and draw a line, and with that line, I hit most of those points. So that would be a fairly strong relationship. With this second one, I could draw a line, hit most of the points, except for this one here. So that would be a linear pattern. It would be a positive linear pattern, actually, with one deviation. The one below here, we see negative relationship, and it's a fairly strong one. And then this next one, it's another negative linear relationship. So I can draw a line and hit most of them, but there's a few points that are a decent amount away. So it's a weaker relationship, but it looks like there's a relationship. Now, with this one off to the right side over here, we could try to draw a line like this, but then we're missing quite a few of them. It almost looks like we could draw a line like that and hit a couple of them. But we could also draw a line like that and be really close to a couple of them. So we're not really sure that there's a pattern going on here, at least not a linear pattern. And so for this one, we would probably guess that there's no relationship. But by looking at them, all we're really able to do is give a guess. And so this chapter, we're going to kind of figure out, okay, how do we get a decent guess as to what's going on? And then once I have a guess as to what's going on, how do I test it if I'm thinking that there's a relationship? So as a statistician, we want to find the equation for the line that best represents the data values. Lines are going to be given in the form of y equals a plus bx, where a is the y-intercept and b is the slope of the line. And I know it looks different than what you're used to from college algebra. College algebra, you're typically thinking y equals mx plus b. And you're like, why are you changing things for me? That's not fun. So the reason that I'm changing the format for you and saying y equals a plus bx instead of y equals mx plus b is because this is the format your calculator is going to give you. And so I want you to be comfortable with the format that your calculator is going to give you. That way you can interpret what the calculator gives you a little bit more quickly. So there's a function on the calculator that we use to compute the values for a and b. And that's found going to stat, then over to calc, and then linreg a plus bx. Now, this formula, this function is nice, and it gives us this line without us having to perform a hypothesis test, which is great and wonderful. But for most of the problems you're going to do in this class, you're going to have to perform a hypothesis test. So while this function is useful, you actually may not end up using it very much. But if you're just wanting the line, not caring about hypothesis test, not caring about how strong the relationship is for the lines, your correlation coefficient, then this is useful if you're not wanting the other stuff. But if you want the other stuff, we need a different function. So I'm giving this to you, but you actually may not use it, is all I'm saying here. So when do we actually want to find these regression lines? Because it's not like when we have something that looks like a bad relationship, we're going to want to find the regression line. So we only want to find the line when it looks like the data has a linear relationship. We visualize that with a scatter plot to begin with. And if it appears that there's a relationship, then we would say, okay, let's find the regression line. But that's not telling us how good the relationship is. And it's not even telling us if it's an actual relationship. So we might want some better methods of looking at it. And we need some way of measuring how strong of a linear relationship we have. So those are some things that we're going to be trying to aim for getting. And in fact, on this next slide, we're going to start talking about the strength of relationship between variables. So we have a statistical tool that measures the correlation between two variables. It's called the correlation coefficient. It's kind of a big idea in this chapter. And the correlation coefficient is found by this formula, which is not super easy to compute by hand. You could, and if you have a small data set, it's not bad. But what you're doing is you're taking all your x's times the y's that they're paired with, and you're adding those up. And then you're adding up all of your x's, adding up all of your y's, multiplying those things together. In your denominator, you're doing x's squared and then adding them all up. Adding up all your x's, squaring them. Squaring all your y's and adding them all up. And then adding up all your y's and squaring them. So that's going to take a little bit of work. If you have a small data set, it's not bad to do by hand. If you have a large data set, not necessarily fun. We're actually going to be able to calculate this with the calculator when we do our hypothesis test. So we're not going to worry about calculating it by hand. We're not going to calculate by hand, but I did want you to see the formula so that you would know what's going on with your calculator and what it's doing. So what is this correlation coefficient besides some messy looking formula, and we're calling it R? So the correlation coefficient tells us how strong the linear relationship between x and y is. The value for R is always between -1 and 1. When R is equal to 0, that means there's no relationship. R is equal to -1 means a perfect negative relationship, and R equal to 1 means a perfect positive relationship. The closer the absolute value of R is to 1, the stronger the relationship. So it's like we have a little bit of a spectrum here that we can be along. We have -1, 1, here's 0. No relationship there. Here's a positive relationship. Here's a negative relationship. Now, we still don't know at this point where along this spectrum we're going to start saying, I'm just going to put a smiley face for a relationship. The one side doesn't look smiley. There's a smiley. All right. So we don't know where this point of R is going to be for saying that there is a relationship. We're not sure where that is, but there's some value there between 0 and -1, or between 0 and 1 that we're saying, okay, we're far enough away from 0 that we can call it a relationship. Okay, all right. But we know that the closer we are to fitting a nice pretty line, the closer we are either to -1 or +1. -1 is going to mean that we have a negative slope to our line. +1 is going to mean we have a positive slope to our line. The less fitting to a line we are, the closer we are to 0. So in this next slide, we're going to see 4 different scatter plots and 4 different values for R, and we're going to try to match them up, and you're going to get to do this on your homework as well. All right. Now, when I see a problem like this, I tend to say, okay, let's focus on the ones that are closer to 1 or -1. Those are going to be the easier ones to figure out first. So looking through these, it looks like the bottom left is fairly close to being a line, and it looks like it has kind of a positive slope going on here, right? That's decently close to being a line. It has a positive slope, so we would probably guess that that one is A. The one on the bottom right looks like it's pretty good at being a negatively sloped line, so we'd guess that this one's probably D. So we've taken care of those. Now we need to work with the ones that have weaker relationship. Okay. So we have weak relationships. We need to have one that kind of has a positive slope, one that kind of has a negative slope. So looking at our other two pictures here, the top left, for the most part, it kind of follows this trend like this, right? In fact, we could kind of draw two lines that most of our data is kind of in between there. We have positive slope. So I would say that this one would be B. Now, let's verify that this other one looks like it has more of a negative slope than a positive slope. Looking at it, some sort of line like this would kind of fit everything because we're thinking, okay, everything's kind of between here and here. It's a negatively sloped line. So we would say, yeah, that looks like C over here. So there's a little bit of guessing as we're interpreting and analyzing what's going on with these scatter plots. And let's just check real quick. Hey, we got all of them right. A, B, C, and D going around. So now we kind of have an idea of what it looks like to have these different correlation coefficients. And the correlation coefficients is just saying how strong of a relationship, how close to the line are all of our points. Now, the big question though is how good are these lines going to be at predicting? Because it's great and fine if we know how strong a relationship it is or not, but how good is this line going to be at predicting things? You say, okay, it's a cause and effect relationship. So what if you gave me an X value? I should be able to give you a Y value then, right? Okay, well, we need to know how good we are at predicting. So the regression line can be used to predict Y values based on X values. When we have a stronger relationship between X and Y, the predictions are better, which makes sense, right? We have a nice mathematical way of actually stating how good they are. So R squared, our correlation coefficient squared, is going to be something called the coefficient of determination. The coefficient of determination is found by just squaring your correlation coefficient. And instead of writing this as a decimal, it's commonly written as a percent. So let's say that you had R equals 0.9. That means R squared equals 0.81. So 81%. So what that means is 81% of the variation in Y is determined by X. So 81% of our value of Y is determined by X. That means 19% is determined by something else. So there's something else going on that's coming into play here. Now, if we changed R to 0.8, which 0.8 we'd say is pretty strong, right? That means R squared's 0.64. So only 64% of Y is determined by X. Well, we want our predictions to be pretty good. If we're getting down to just 64% is determined by X, is that good enough? That has us start making a kind of doubt our initial guessing as to how good Y needs to be, how good R needs to be, how big it needs to be, or close to 1 or -1 it needs to be for us to say that this is a good relationship. So let's actually talk about the hypothesis testing to determine if we have a strong linear relationship or not. So from gathering data and computing the line of regression and the correlation coefficient, we can't statistically state if there's a relationship between the two variables or even how we can say how strong it is, but not if there's actual relationship. We can say it looks like there's a strong relationship, but we have to do a test to actually state that there is one. If the correlation coefficient is strong enough that makes us think there could be a relationship, we would probably want to test and see if that's true. So we need to know how to do tests on correlation coefficients. And so what we're doing is we're performing a test on the correlation coefficient to see if we think the population correlation coefficient, rho, rho is a Greek letter that kind of looks like P. It's kind of fancy. So we're testing to see if rho is equal to 0 or not. So if it's equal to 0, that's saying no relationship. Not equal to 0, we're saying there is a relationship. So our hypotheses are saying that rho is equal to 0, not a relationship, or rho is not equal to 0, there is a relationship. Our degrees of freedom is n minus 2, and we're actually using the t-distribution here to do this. And I'm not going to get into the theory behind why we end up using the t-distribution. Google it, YouTube it, or email me if you have questions about why we use the t-distribution. Just know that we are. When you're writing your hypotheses, you don't have to write the sentence next to it. You just have to write our symbols there that I've boxed. I tend to write that sentence next to it, or at least an abbreviation of it, saying relationship or not relationship, just so that I remember what I'm doing when I go to write my conclusion sentence at the end. It kind of just helps remind you of what's going on when you're getting to the end. Sometimes when we get to the end of the problem, we try to rush a little bit, and that kind of saves us from making a silly little mistake. So 5 steps for hypothesis testing, same 5 steps that we've been going through. State your hypotheses, identify your claim, state your level of significance and your critical value for the traditional method. Find your test value and the p-value for the p-value method, make your decision, and then write your sentence. Making your decisions made the same way that we've been making it. So compare alpha and p. Alpha less than p, do not reject the null hypothesis. So let's do an example here. So we have a student that wants to see if the number of times a book has been checked out of the library in the past year, the number of pages in the book are related. She's hoping that the number of times a book has been checked out of the library in the past year could be a predictor of the number of pages it has in it. She's randomly selected 10 books from the library. Let's test her claim at a 0.01 level of significance. Maybe she's hoping, to find a really short book, and she's saying, okay, if it's been checked out a lot more, then maybe it's a shorter book to read. So let's go through, let's look at her data, and let's create a scatter plot to kind of look at it. So scatter plot, we would have X's and Y's. Since she thinks the number of times it's been checked out is a predictor, we would say, let's go back, I pressed the wrong button. We would say that this is X and this is Y, and we would draw a scatter plot. Now, the less data you have, the harder it is to see if there's a relationship or not. Looking at this, it kind of maybe looks like we could draw a little bit of a line like this, but there's quite a few data points that aren't very close to the line. So maybe it's not quite a linear relationship. There's a chance that it is. So this looks like something we would definitely want to look into a little bit more. Before I go to the next slide, I want to make sure that you guys all have your data either in your calculator written down or a picture taken of it. So make sure that you do have this data ready to go. When we do our test, we are going to want the X values in list 1 and the Y values we would want in list 2. Okay, so it doesn't appear to be too strong a relationship or correlation, but we're going to go ahead and compute the correlation coefficient in the regression line and test to see if there's a relationship or not. And we will see what it is. So, looks like I went ahead and carried the data over to this next slide. That's wonderful for us. So we have our data here. We have list 1, list 2, and we type those into our calculator, list 1 and list 2, and then you're going to go to stat over to test, and you're going to want the lin reg t-test. And with the lin-reg t-test, it just wants to know where your x list is, where your y list is. So list 1, list 2. Frequency, leave that at 1, and then symbol. So you'd need to enter your symbol. For these tests, we're always going to have not equals as our symbol. So let's go ahead, type all of your stuff in, pause if you need to, if I'm going too fast for your typing, but we go ahead and hit calculate. Oh, by the way, reg EQ. Leave that blank. That's just asking what your regression equation is. We don't have any guess as to what the regression equation is, so we're going to leave that blank for now, and it's going to calculate a regression equation for us then. But so by typing our list 1, list 2 in and performing the test, we'll get R. R is negative 0.0936. So it's actually a lot smaller than what we thought it was. But it is a bit of a negative slope, which is what we had drawn. So we had something going for us there. And then we're able to find what our equation would be as well. So plugging in A and B from what we get from our calculator, we find that y equals 324.513 minus 0.3523x. Our hypothesis test, we're testing row equaling 0 versus row not equaling 0. Row not equaling 0 is a claim. We're claiming there's a relationship. In step 2, we're listing alpha. We're listing our critical values. Critical values are being found from T. And I listed how to find degrees of freedom and stuff like 2 slides ago. And so that's how you can find your critical values if you want to. And then from your calculator, you got T is negative 0.266 and P is 0.797. So from that, we compare alpha and P. Alpha is smaller than P, so we do not reject the null hypothesis. So we'd say there's not enough evidence to support the claim that there is a relationship between the number of times the book is checked out and the number of pages it has in the book. And that's it. That is all there is to chapter 12. If you have questions as you're going through the homework, do make sure that you email me. Otherwise, I'll see you in the next chapter.